Okay, so welcome to this afternoon session of third day's program. Today it is my turn. I thought listening is much better than lecturing, right? Yeah, I've been very sincerely attending all the lectures. Every minute I have attended. Okay, fine. So that's good. It's learning for me also. So what I'm going to do today, I've already said in the morning also. So we are going to start with what is least square method. We will solve some problems using least square method in Sage. I'll also introduce SVD, singular value decomposition. Singular value decomposition is one concept in linear algebra, which is very powerful. At the same time, I think anything you would like to know about matrix, it is there in singular value decomposition. Please, all of you mute yourself. Ambika, is it possible for you to mute in case people are keeping their audio on?
Yes, sir, I can.
You can just check whether you can.
Yes, yes.
Otherwise, I'll make you host so that you will have that control. Maybe I'll make you host.
Sir, as a co-host, also I can mute.
Okay, fine. That is good, great. But in any case, I think I'll make you co-host. So you please make me host to co-host. I'll make you host. So that when I'm lecturing, I made you co-host. So you make me co-host so that I will also have some control at least. Right. So first I'm going to explain briefly least square method. So let me first share something on which I will write and explain rather than just showing you what. And then I will also share a Google Sheet in which whatever program I am writing, it will be there. Apart from that, I have already uploaded all the handouts that I'm going to use, including the data file that I'm going to use in day 3 of Google Classroom. So you can look at them. We will make use of those things. I'll tell you which file we are making use of. So I have not, I have made them HTML file and uploaded in the Google Classroom so that you can open if needed, you can copy and paste it in the worksheet, either Sage worksheet or Python worksheet. So first I'll use Sage for least square method. Then for singular value decomposition, I'll make use of Python itself. One can use Sage math also, but I have prepared in Python. Right. And then in case time permits, I'll also look at what is called clustering method, which is very simple method of classification. That worksheet is also already there in the Google Classroom. So in case we are not able to cover, you can have a look at it and then work it out. Okay, fine. So let me share my screen. So first, let me share this OneNote in which I'm going to write. Okay, so let us start with already, I think Professor Krishnan introduced what is least square method in general. So what is it? So basically, see many concept in linear algebra amounts to solving system of linear equations. So let us start with this system of linear equations. Let us assume that A is, let us say, M cross N matrix, and I will write columns of A as, let us say, A1, A2, dot, AN. So each AI is a vector for me. This is a vector in, it has M coordinates, so it will have vector in Rm, right? And as a result, B also has to have M components, so it is also vector in Rm. And X is X is variables in Rn. So I'll write this as x1, x2, dot, 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 xn. Okay, so this is what we want to solve. This equation, it is quite easy to see. I can write this Ax equal to B as x1 times A1 plus x2 times A2 plus dot, 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 xn times an. This is equal to B. This we can write this equation in this form. Is this clear to everybody? Is this clear? If it is clear, you can click yes. Otherwise, no. Or if you have some question, you can raise your hand. This is quite simple. I'm sure most of you must have seen this. Right. So fine. That is Ambika, you can also clear the response once the question is answered. Right. So this is one way. This also means that suppose if I say, let us say alpha, which is alpha 1 up to alpha n, if this is a solution, just 1 second. Hello, Swagata. Sorry, I think it was a call from one of the speakers who is going to talk in this evening. Right. So yeah. So if alpha, which is alpha 1 to alpha n, is a solution of, let me give this a name. I'll call this as, let us say, star. If this is a solution of star, this simply means that this B I can write as alpha 1 A1 plus dot, 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 alpha n an, alpha n an. This simply means that B is a linear combination of A1, A2, An, and that simply means that B lies in the column space of A. Please mute yourself. B lies in column space of A, or that is nothing but linear span of these vectors A1 to An. This is what Professor Krishnan mentioned, right? So that is what it means, right? Now, that is one. So in case Ax equal to B has a solution, that solution will be in the linear span of this. The question arises if this is not the case. If this is not the case. Now, if you also know that if I look at this image space of A, see, by the way, here A is matrix which is M cross N. So this is a function, linear function from Rn to Rm. This is a linear function from Rn to Rm. In fact, that is how matrix we can visualize. It's a map that takes vectors in n components to vectors in m components. That is the transformation, right? So any data that we are looking for, and when we want to transform in linearly to some other space, there is some matrix involved. Okay, right. So this is image of A, which is nothing but column space of A, and all these things we can compute very easily in Sage, that we will look at. Okay, this we know that this is a subspace of the image which is Rm. So let us look at, I have, this is my Rm. Let us say this is my Rm, and I have some subspace. Generally, I'm not good at drawings, but anyway, you have to just visualize that this is something. This way. Okay, so this is my image space of E. And in case B is a solution, B lies in the image space of A, this has a solution. Otherwise, this is what will happen. So let us say B is this vector and this is not in the image. So if B does not belong to the image of A, then what is the question that we can ask? Then if it is not in the image space of A, we have to look for what is the best that I can do. Right? This is your target. Your target is to be in B wants to be in the image space of A. That's your target aim. If you cannot achieve that, what is that you would like to do? You would like to do, or you would like to be as close as possible. That's a natural thing, right? Right? If you look at any innovation, then they will try to be as close as to the kingdom which they want to kind of invade. Right? So you want to be as close as possible. So you want to look for something here. Let us call this as some P, such that this distance is as small as possible. Right? P is in this, but if P lies in here, P is going to be of the form some A times, let us call this as X star. P is going to be in the image of A, so it will be some this for some X star in where? In Rn. Right? That is what it means. So this is what this X star is what we call least square solution. And what will be P? P also has some name. Can somebody tell? What is P called? You can unmute and tell. Any of you?
Foot of P, sir.
Foot of what?
Foot of P, P.
P is a point. So what do you mean by foot of P?
Means
P has got some name.
See, perpendicular, sir. PP is perpendicular to that, sir.
It is?
PP is perpendicular to the bottom.
Okay, right. P is going to be perpendicular. That is fine. So in terms of B, what do we call P as?
Image we can tell, sir.
No.
So reflection?
No, cannot be reflection.
Projection?
It is orthogonal projection. Very good. Very good. It is orthogonal projection. Right? So P is this is nothing but orthogonal projection. Gonal projection. And orthogonal projection, all of you must have seen in your course in linear algebra how to define orthogonal projection of a vector onto subspace. Right? So this P is nothing but orthogonal projection. So this AX star I can obtain once we know what is the orthogonal projection. Right? X star I know what is orthogonal. I know once we know what is P. Right? So X star is called least square solution, but AX star is nothing but orthogonal projection. So this finding least square solution is nothing but finding orthogonal projection of B onto subspace image of A. So suppose I call W as image of A, that's a subspace of Rn. That's a notation for subspace. And you must have seen in inner product space Rn. So let us say for all these things, we will assume that Rn has inner product, which is standard dot product. Okay. So this W is a subspace, and you must have seen that in this case, we can write Rm as W plus W perp. Right? And that is same as saying, if I take any vector X in Rn, then I can write uniquely as X is equal to some W plus W dash, where W belongs to capital W, W dash belongs to W dash, W perp, I should say, W perp. Okay, so that's the the thing. I mean, and you must have also seen how to find this W and W dash explicitly. I'm not going to go into those things, but one can very easily do. The way to do is you generate some orthonormal basis of W, extend it to the orthonormal basis of RM, and that's it. That's the basic idea. But this, all of you must have seen as a theorem in linear algebra, maybe also in functional analysis if you have gone through course in functional analysis, right? So you see that that's a geometric meaning, and that's a real life problem we have. Unfortunately, if in linear algebra, it will just as a theorem with no application in most of the books. Okay, right. So that is what we want to find. Now let us look at how do we find. Is my voice proper?
Yes, sir. Yes, sir.
Because I thought it is low. Okay, fine. So how do we find this? So now what is that? P is what? P is the point in the space, image space, which is closest from B. So the closest from B, how do I define? I can define, take the difference of A, X, any point AX, any point in the W is going to look like AX for some X, minus B, take the distance of this, which is norm, and you minimize this. You minimize this. But then when we want to talk about minimization problem, most often we look at calculus concept, and in calculus, when we want to use, we would like to use derivative, and I'm sure you know that norm is not a differentiable function. So instead of this, we will calculate this square. So let us write this as minimize this, but minimize this over what? Set of all vectors X in Rn. Minimize this. So if you find X for which this is minimum, this X star, or let us say you call this as a function, right? You minimize this function, and that is what if X star is a solution or is a minimizer. Let me just put that, is a minimizer of norm X minus B the whole square, then X star is called the least square solution of X equal to B. That is the definition, right? So the problem has now reduced to a minimization problem, something which this morning you saw. It is a purely calculus problem now, which can be very easily solved using calculus. Okay, which can be very easily solved using calculus. Okay, so now let us look at. Now, let us see if we have this is what we want to solve. Okay, this is what we want to solve. But let us assume now, if I say my M is bigger than N, so I have more equations than number of variables, it may not have a solution, right? It may not have a solution. So let us assume that. Also assume that rank of A is, let us say, N, maximum. This is maximum. So A is maximum rank matrix, maximal rank. Okay, the rank is A is maximum, because the maximum, the rank is going to be less than equal to minimum of M and N, and if it is equal to N, it is maximum. It cannot have more than this. Okay, so so if the rank of A is N, now if you look at A star, A transpose A, what is order of this matrix? What is order of A transpose A? What is order of this matrix?
N cross N.
N cross N, very good. N cross N. So what will be its rank then? What will be rank of A transpose A?
Maximum n.
It will be actually
Less
n.
than
You
or
can
equal to.
you can show that it is going to be n. This you can look at. I'll leave this as an exercise. I'm sure most of you must have seen this. It's a standard exercise in linear algebra. Okay, so this has rank n. But if this has rank n, what does it say? A transpose A is invertible. A transpose A is invertible. Now that tells me to do something here, right? That tells me that I can do something here. What can I do?
So pre-multiply by A transpose, sir.
I can multiply both sides by A transpose. Very good. So I'll multiply this by A transpose. A transpose AX is equal to B. Now I have not done anything here. I multiplying this A transpose A is nothing but it's just a kind of doing some scalar multiplication of these equations, right? So if X is a solution of this, it will be a solution of this. So any X which is solution of this equation star is also going to be a solution of this double star, right? And so this is what is called normal equation of star. So if in order to find actually what I'm saying is not exactly correct. In order to find yes.
So sorry to interrupt.
Hello,
But, it should be A star be on the A transpose be on the right hand side, no?
This of course. That's correct. Thank you. Both sides we are multiplying, right? So in order to find least square solution of this Ax equal to B, we need to solve is this normal equation. That is very easy now because we know A transpose A is invertible. So what will be solution of this? What is solution of this one? I can multiply both sides by its inverse. So I can write this solution. Let me write this solution X star as A transpose A inverse A transpose B. That is a solution. So this is one way of getting the solution. Is this clear to everybody? Is this clear to everybody?
Yes, sir. Yes, sir.
In case you have any doubt, please ask. I am not in any hurry.
So
Okay.
clear, sir. Yes, sir. Yes, sir. Understand, sir.
Okay, very good. Right. So this is a solution. Let me just quickly also indicate this, which we have. Let us say I call this as fx is equal to norm of ax minus b the whole square. This is what we want to minimize. If we want to minimize this, we'll have to take the gradient of, find the gradient of f of x, equate it to 0, and then solve for x. That is how we do. And then you can find Hessian of this. Right. So one you can easily look at this. You can just multiply. We know that this is going to be same as ax minus b transpose into ax minus b. That's your f of x. So it's just this is transpose. That's a matrix multiplication. So you multiply and expand this, and then find grad f equal to 0. This from this you will be able to show that x is nothing but A transpose A inverse A transpose B. So that's also the same thing you will get using calculus. So we have here some simplification is required, and then you will see that this is nothing but a quadratic, which you can very easily differentiate with respect. Of course, we have to differentiate with respect to x. So your look gradient of f, you can find it component wise, but it turns out that this is nothing but 2 times A transpose A is equal to A transpose B. Right. Okay, fine. So 2 will get cancelled. You'll get this solution. So this is actually calculus based, and that's actually why the name least square. Okay, so you're applying this, right? So this is one. Next, one can also show that you see this. You have Ax equal to B, right? This is what you want to solve. In case A is invertible, we know that the solution is A inverse B. If A is invertible, we know the solution is A inverse B. But if A is not invertible, you can talk about something which is called generalized inverse or pseudo inverse. Right? So you must have seen this. This is what we call a generalized inverse. Generalized inverse. I'm not going to go how to define these things, but we will look at this using singular value decomposition. It will be clear. Okay, so this if this is the generalized inverse, it turns out that X star, the least squared solution, is nothing but generalized inverse of A times B. Generalized inverse of A times B. Okay, so if we know how to define generalized inverse of a matrix, which could be could be singular matrix or any rectangular matrix, we can always define its generalized inverse. Then this will be the solution. So we can find least square solution using calculus, using pure linear algebra as a orthogonal projection, as a again generalized inverse, using generalized inverse. Okay, right. So we will do this, but let us look at this. This problem is also many times one can think of this as a best fit problem. So let me quickly describe that, then I'll go to this SVD. Okay, so suppose you have set of points. Let us say I have got some set of points. This is my set of points. Don't worry about the coordinates, etc. And you want to, let us say, fit some kind of polynomial to begin with. Let us say this is a polynomial. This polynomial is, let us say, y is equal to px, where px is a polynomial. Let us write this polynomial as maybe an x to the power n plus an minus 1 x to the power n minus 1 plus dot 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 a1 x plus a0. This is x. This is a polynomial you want to fit. Okay, this is a polynomial you want to fit. So that means you want to find these parameters an minus 1, a1, a0, such that this is best fit. Now one has to define what is meaning of best fit. What do you mean by best fit? So I'm so sure many of you must have already seen. Yesterday he also defined, except that he defined using perpendicular distance. What we can do is, so you can also think of, if you are a physicist or engineer, you will think of this as a kind of fitting a model to the experiments that you have done. So these are your data coming from the experiment. Let us say this is your data, which is xi, yi. So you have done some experiment, you have got output yi at the input xi, right? So this is, so if I look at this perpendicular distance of this, if I look at this perpendicular distance, if this model px passes through all my experimental points, then this point would have been here, right? What is coordinate of this? This coordinate is nothing but x. This is my xi. So this is xi pxi. This is xi pxi, right? So this I will call this as error. This is the error term that you have done. You have committed while doing the experiment at ith input point. Okay. So what is this error? This error. Can somebody tell me what will be this error? Vertical distance.
yi minus p of xi.
Yi minus p of xi. Is this correct? Can somebody suggest something?
Absolute value.
We'll write absolute value because we are talking about error. This point could have been above this curve or below this curve. So this will be error. Okay, so this is the error that you have committed, how far you are from this model. So that's your model. Okay, so this we have to minimize for all the points. So in order to minimize this, I can take the sum of all these. But then again, if I want to minimize and then we want to use calculus, we can take the square of this. We can take square of this. This we have to do it for each and every point. Suppose there are n points, I'll call this as 1 to capital N. If there are capital N points, you have to do it for everything, right? So what will this be? You are finding Px, right? So that means this is actually a function of these variables. Let me put this as an minus 1 up to a1, a0. This is a function of this. So this is what you want to minimize. So your aim is to minimize f of an, a0 over all this xi. So that is again minimization problem. Now look at this. Can I write this in terms of the matrix norm, which we norm in terms of ax minus b, the one which we did earlier? The answer is yes, because these are the n coordinates, right? So you can think of this. I can think of this summation. Let me write it below. I can think of this summation yi minus pxi norm of square, or simply square is same as norm square. This as what? Norm of this my first vector is going to be y1, y2 up to yn. This is this minus this is going to be px1, px2 dot pxn, right? P capital Xn, it should be capital N. Is that clear? So this minus this matrix and norm of this square. Okay, that's what we have well done, right? And this pxi, this, so let us call this as y, right? So I can write this as y minus this px1, px2, pxn. You can also write this as, see, what is the px1? What will be the first row of that? It is an xn, an into xn, sorry, x1 to the power n plus an1 minus an minus 1 x1 to the power n minus 1 and so on. So I can write this as an sorry, not this way. This will be the matrix in x1 to the power n, x2 to the power n dot xn to the power, I should write capital N, keep forgetting, to the power n, and this side last one will be x1, x2 dot xn, and then 1 dot 1, this times an minus 1, a1, a0. That's what. So this is, so you can think of this as a. This is your x, now variable, the norm of this square. Is this clear to everybody? Have you understood?
Yes, sir.
Okay, so we have converted this problem of best fit polynomial, and though we have taken polynomial px, you can take any function, except that the complexity of solution may become very hard. It may become very hard to find the parameters, but one can do. Okay, so now we have a and this x. So this is now nothing but norm of y minus ax whole square. Here, what is y? Y we know, y12, yn, we know a. We also know what is x. Okay, right. So we know. So finding this best fit solution is nothing but solving this equation, and we already know what is the solution of this. So in this case, we know that the solution, which is x star, is nothing but A transpose A inverse A transpose B. except that once we assume that this is invertible. This is invertible is just same as saying this, the columns of A are linearly independent. Columns of A are linearly independent. Okay, so that you can geometrically also tell what is the kind of points that you are expecting. Okay, fine. Right, so this is about least square solution. So we will solve these problems in a minute in Sage. Okay, is this clear to everybody? What is meaning of least square solution and how to solve them? Out of 60 people, at least I should get 30 yes. I have only 9 yes. So that means no chat for this kind of thing. Otherwise, it will be difficult to manage. Okay, so fine. So this is one. Next, let us look at what is singular value decomposition. Quickly, so that we can singular value decomposition. In short, SVD. Okay, you can find out history about SVD. I'm not good at those things. As I said, this singular value decomposition is one concept which is very useful, has lots of applications. So if I want to, let us say, dissect any matrix, right? You want to know anything about the matrix, if you do a singular value decomposition, that's it. You will know everything about that matrix. And it has a lot of applications, including applications in data science and many other fields, including in image processing, right? So it is very nice concept. Unfortunately, it is
Hello.
not. Yes.
Sir, if time permits, could you discuss few applications based on SVD?
Madam, that is what I'm going to do.
Okay.
I have been telling from yesterday.
Okay. Okay. Thank you, sir.
Yeah. Okay. So the yes, little bit of theory Professor Krishnan here already did. Right. So what does it say? Let's not go into this. It says that you take any matrix, let us say m cross n matrix. Let us stick to real matrix, but one can do it over other fields also. This is m cross n matrix. Then you can split this as a matrix U times a matrix, let me write that as sigma, or maybe S, but S stands for sigma. Okay, let us write this as sigma times V transpose, where this U and V, they are orthogonal matrices. Orthogonal. This also is orthogonal. And we know what is meaning of orthogonal. Yesterday also we saw. And this will be a kind of diagonal matrix. It may not be diagonal exactly, because this can be any rectangular matrix, right? So this is what it says. Of course, you know that in case you if A is diagonalizable, then already you know what is U, what is V. U can be written as column matrix of rather V transpose can be written as column matrix of eigenvectors of A. And say this is going to be diagonal matrix of eigenvalues, right? Okay, so that we already know. And in that case, V and U will be transpose of each other, the inverse of each other, right? That's already we know from the diagonalization. But if it is not diagonalizable, or if it is rectangular, then we cannot apply that. Okay, but anyway, so this is one. Now let us write U By the way, this already, I think the names, etc. Yesterday it was told, but it is good to compute in case this happens, then you can compute what is A transpose A. What is A transpose A? This is going to be U sigma V transpose times. By the way, I should also tell there are other many ways of writing this, but let us say this will be M cross M matrix. This will be M cross N matrix, and this will be N cross N matrix. So U and V are square matrices. This, okay, this is times the transpose times U sigma V transpose. If you calculate this, if you simplify this, what is that you are going to get? This is going to be U sigma V times sigma transpose U transpose times U, and U transpose U will be identity matrix. So what are you going to get is V transpose sigma this times what? Last one is V transpose. Wait. First one is not V transpose, right? Because it will become transpose of transpose, which is V into V transpose. Okay, you can correct in case I'm making mistake. Is this clear? Now, what does it say about what is this? What is order of this sigma transpose sigma? What is order of sigma transpose sigma? Sigma is M cross N. So sigma transpose sigma is going to be N cross N. This is going to be N cross N, right? And this is going to be diagonal matrix. In case this, I did not write the sigma explicitly, but here this sigma, let me just write it here itself, is going to be of the form sigma 1, sigma 2, dot, sigma r, remaining all zeros. Okay, M cross N, and these are all remaining zeros. And we also here we have sigma 1 greater than equal to sigma 2, and so on, sigma r. So these are all arranged in decreasing order, and r is rank of A. These are the assumption. Okay, right. So this is diagonal matrix, and you are diagonalizing using this orthogonal matrix. So it says that this is diagonalizable, and naturally it will be diagonalizable because it is a symmetric matrix, right? So it is diagonalizable, and it says that, and not only that, it says that the eigen vectors of A transpose A are going to be the diagonal entries of sigma transpose E, which is going to be sigma 1 square, sigma 2 square, and so on. So it also means that you can find these sigmas using finding eigenvalues and eigenvectors of A transpose A. Similarly, you can do A transpose A. You can do this calculation. Okay. So this, and that is one reason. If I write U as U1, U2 dot U, it is M cross M, so UM, and V as column matrix V1, V2 dot Vn, this is N here. Then these are going to be orthogonal vectors, and these are called left singular eigenvectors of A. These are called right singular eigenvectors of A. Okay, and these sigma 1, sigma 2, sigma r, they are called singular values. That is why this name singular value decomposition. These are called singular values. Okay, so it actually tells me that the A we can transform into this, and this is orthogonal matrix, which is easy to visualize, handle, look at the transformation. This is kind of diagonal matrix that again we know how to handle. This is again orthogonal matrix, so it has simplified. That is one part. Of course, he mentioned how to explicitly find these U and V, but here you already have the process. What you are going to do, you are going to find eigenvectors of A transpose A and write that as a column matrix of V transpose. Similarly, this side will give you U. Okay, so you find eigenvectors of A transpose and write that as those eigenvectors as column vectors. And in case it's possible that you may have to extend to a orthonormal basis of Rm and Rn, depending upon the size of these matrix that you have to do. Okay, I'm not going to complete detail of those things. Okay, I'm sure you can find out, right? So this is how we can find U and V, right? So of course it also tells me that it is not going to be unique. At least ordering you can do in any order. So that is uniqueness is also not there. Okay, but let us play further with this decomposition which we have got. What we have, A is U sigma V transpose. So that we will write as column matrix U1, U2 dot 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 UM times sigma. Sigma I have is sigma 1, sigma 2 dot 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 sigma R and remaining all zeros. This into V transpose. This I can write as V1 transpose, V2 transpose dot 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 Vn transpose. Let us write it this way. So if you expand this, what will you get? This is block matrix multiplication. This you can write, it's quite easy to check. I can write this as sigma 1 times U1 into V1 transpose. Let us not write this summation at present. I'll write summation later. Plus next component is going to be sigma 2 U2 V2 transpose plus dot 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 sigma n. Sigma, it will stop at sigma R because remaining all going to be G. Sigma R UR VR transpose. You can check that this is going to be M cross N matrix. This is all M cross N matrix. These are all M cross N matrix. What have we done? A is this. We know what was rank of A? R. What is rank of this matrix? What is rank of this? U and V are orthogonal. They are non-zero vector, definitely, because matrix U is orthogonal.
So,
what will be the rank of this?
1, sir.
It is 1. This rank is 1. Each term has rank 1. So you have split rank R matrix into sum of rank 1 matrices. And we also know that this sigma 1 is of maximum size, maximum magnitude. Of course, it is non-negative. One can show that it's non-negative. So it is maximum. So it's also possible that sigma R, when you go along, it will be very small. So the maximum informations are contained in first few terms. Remaining possibly can be ignored. In case R happens to be very, very large, the maximum rank will be, maximum is going to be in this. So that is an application of what is called compression. So now imagine, suppose you have some image. This is my image. Some large image, few thousand by few thousand, right? And any image, we know that this consists of a matrix. So this is a matrix. Any image is a matrix whose values are pixels. So I can read this as a matrix. And then I can write this as singular value decomposition. Okay, I can write this singular value decomposition of M. Right? And then I can just take first few terms. And that will give me most of the information about the image. So instead of taking entire matrix M, I can take only first few terms, which will tell me about, almost everything about the image. That means really this approximate image is going to be very close to the actual image. So that's the image compression. Okay. Again, we will look at this in Python. Actually, we will look at an image, convert this into matrix, write the singular value decomposition, take first few terms and see how it approximates. So that's what if you look at, let us say, if I have to send some image which is very, very high quality image, very high definition image, its size will be quite large. Even these days, mobile has very good quality camera. Mr. Mohan, please mute yourself. It has very high quality camera. So if I want to send this image to somebody else, instead of sending the entire image, which may take a lot more time, right? We can send the compressed image. The same thing the satellites can do when they take picture on some planet and it has to send to the ground. Okay, so that's that's an application to singular value decomposition. One more thing, let us look at. What was this A? A is U sigma V transpose. A may not be invertible. A is a rectangular matrix, so it may not be invertible. But then we can find it generalized inverse. So if I want to find generalized inverse of A, this will be same as generalized inverse of this. But and in case A happens to be invertible matrix, its generalized inverse should be same as its inverse. You want to generalize, so it has to obey whatever is existing, right? So by rules of inverse, this should be generalized inverse of V transpose, generalized inverse of sigma times generalized inverse of U transpose. Now, what do you think should be generalized inverse of V transpose? What should be generalized inverse of V transpose? Okay, I think, sorry, I made mistake. I wrote, let it be. So I should write it here. Now it should be generalized inverse of V transpose, generalized inverse of sigma transpose, generalized inverse of U transpose. What should be generalized inverse of this? V transpose. Any answer? V is already non-singular. V already is orthogonal. So what should be its generalized inverse? Has to be its inverse. What is inverse of a orthogonal matrix? It's transpose, right? So this is nothing but V. And this I will write as this, and then this is nothing but its transpose. So already we know this. If I know how to define generalized inverse of this rectangular matrix, which is a diagonal type, we are done. So, and it is quite easy to guess what should be generalized inverse of sigma. What do you think it should be? Also, now what dimension has also changed. This is n cross n. This is m cross m. So what should be dimension of this? This has to be n cross m. Earlier it was m cross n. Now its transpose is m cross n. So it tells me that I have to look at its transpose. Right? We have to look at the transpose of the original one, and then where inverse of a diagonal entries we know. So it will just write 1 upon sigma 1, 1 upon sigma 2, dot, 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 1 upon sigma r, and remaining all zeros. This is n cross m. So take transpose, whatever is the non-zero element, you take its reciprocal. That's it. So this is also gives me how to find generalized inverse. Just now we did in case of singular least square method. Is this clear to everybody? Is this clear to everybody? Okay, fine. 12 people have said yes. Some of you are saying in chat. Let me clear. Fine. So this is application. One application is image processing. One application is you can find generalized inverse. Another application actually geometrically you can find what should be geometry. What is geometrically A doing to any object that can be again obtained because orthogonal matrices rotates. This diagonal matrix will scale along coordinate axis, and this again. So it is rotation, scaling, rotation. So that is another geometric meaning. But all other information, lot of information you can find out about norm, about many things. Okay, I'm not going to get into those details. Anyway, now let us look at how we can find these things in in Sage. Okay, let us now move to Sage and then see how we can make use of. Okay, so I'll stop sharing this. I will disconnect this in case we need it. I'll come back to this so that it doesn't object. Okay, let me stop sharing this and I'll share. Okay, so first let me share my entire screen. Although this is not convenient. This is what. So all of you, this also I will exit. Unfortunately, this one goes. This is something I will share. Okay, so many of you who have installed Sage Math, you must be seeing 3 icons, right? Sage Math 9.3, whatever you have installed. 9.5 is current version, but I think window version of 9.5 is not yet available. Generally, they release little later. So this is 3 icons you will get on Windows. Is there anybody who is using Linux? Okay, fine. Please mute yourself. So otherwise, you can just click on Sage Math Notebook. It will open the notebook in Jupyter, or you can click on Sage Math Cell. Then cell command will also work. So let me just tell you that. So let us say if I say Sage Math, it tells me Sage Math 9.3 cell. So I will click here. This is the Sage Math cell, exactly similar to how it will look in Linux terminal. Here you can type the command. So let me give the command Sage -n Jupyter. This tells me that I am asking Sage to open through Jupyter Notebook. You can also open using what is called Jupyter Lab, which is also slightly advanced version of Jupyter. Okay, or you can change to any directory and then open. That also you can do. You can change to any directory and open. Okay, so let me open this. But in case already if you have started, you can continue to use whatever thing that you have done. There is no problem. There is no problem in that. Okay, right. So now we will let me open a new worksheet. So I will open Sage 9.3 worksheet. This is my. If you want, you can let me give this a name. Let us say ATAL FDP, maybe 2022 lecture 1. And that's the name I have given. This is where we will type. Okay, so let us define a matrix. Suppose I have already you know how to define a matrix. I have some matrix A, which is let us say 7 minus 2 1 minus 1 2. This is my first row. Okay, then second row is let us say 2 0 4. Next row is 6 2 minus 19. This is my third row. Sorry, third row. Yeah, this is how we can type. Okay, let me put this in the Google Sheet so that you can have to see. Yeah. Okay, I'll copy this. Let me share this also. I have not shared yet. I'll just copy this in chat message. Are you getting the Google Sheet? Google document? It's not Google Sheet, it's Google document. Okay. Right, so that's the matrix. Okay, let us come back to this. This is a matrix. Okay, now anything that we want to know about this matrix A, anything, all the concepts that you study in linear algebra, you can get it by just looking at A dot and then tab. A dot and then press tab, because Sage is based on Python, which is object-oriented programming language. all the informations regarding A will be available by this. Okay, some of this you have seen, right? Some of it already you have seen, but all these things. So for example, today we talked about what is row space of A. Row. So you see that row space of A. It says the row space of A is a free module of degree 3 of rank 3 over integer ring, and its basis, echelon basis is this. Similarly, you can find column space of A dot column space of A. Okay, you can find row space of A, you can find column space of A. Anything that you want to do, you will be able to. You will be able to see that. Okay, right. So what anything about A you can find out. You can find out determinant, which we saw. You can find A dot RREF. I think a small RREF. RREF. Reduced row echelon form. Okay, all these things can be done, including eigenvalues, eigenvectors. We have seen already, so I'll not go into. Now let us say we want to find singular value decomposition of A. We want to find singular value decomposition of A. How do we do that? So let us say SVD of a matrix. So let us quickly do this. Okay, so maybe let us start with a matrix M whose first column is, okay, so let us say this is a matrix whose first row is, let us say 1 1 1 1 1. This is my first row. Second row is, let us say 1 2 3 4 5 5. Yes. Next row is maybe 1 4 1 4, then 9 14. I'm sure you know what we are doing. 14 and then 25. And let me write transpose of this. So dot T will give me transpose of this. So let us ask it to show what is A. No, what is M. This is my matrix M. Okay, let me just type it in the Google Sheet. Okay. So show M actually it shows in pretty print form. It uses LaTeX. And in fact, we can generate LaTeX command for this. So if I say LaTeX M, it will give me LaTeX command. Now this I can actually copy paste in. Let us make this this particular cell as markdown. We have seen this in Python. If I make this in markdown, if I type inside, let us say $, those who know LaTeX will understand. It exactly will say. So I can start with this now. The beginning itself. Let me put a cell here and convert this into markdown. So I'll say, so my heading is SVD, and let us consider a matrix. Yeah, so that is the text for me. Okay, fine. So these things I'll not copy in the Google Sheet. Yeah. Right. So what is that? Our aim is to find singular value decomposition of this, right? SVD of this. Now, if you try to do a dot tab, then there is a command called SVD. Then it will give you some error. It says that says dot matrix integer dense something object has no attribute SVD. That's because this when computing a singular value decomposition, it has to do finding square root, and because normalize etc. it has to do. So at present it thinks of the matrix as matrix over integers because we have not mentioned anything. So it will not do. Right. So what first we will do, including for M, what we'll do, we'll convert this into some field which has higher precision and double. So let us write M is equal to M dot change ring, and let us call this as CDF. Yesterday we saw what is meaning of CDF. So I'll not go into this. So let me copy this. Okay. At any stage, in case you have problem, please stop me and ask. Okay, please stop me and ask. I expect all of you to do this along with me so that you become comfortable. And in case you have any doubt, you can ask. I'm not looking at the chat message because it's very difficult to look at all these things. So if you have any doubt, please raise your hand and ask. Vijay, what do you want me to explain again? Vijay? I think you sent a chat message saying that please explain again. Can you?
Hello, sir. Can you hear?
Yes, yes, I can hear you.
Sir, that CDF part, that change ring CDF, can you please explain?
This simply means that see, yesterday we saw what is CDF, right? This is it is complex double field, right? With very high precision. So it is just changing the domain on which the matrix is defined. Okay, that is the meaning. So
Okay, sir, thank you.
Even if you have defined matrix over integers or over rational or over real, you can at any stage, if you want, you can change its the entries parent. Okay, that's what it means. Right, now we can find out M dot SVD. M dot SVD. This is, so it has three things. First, so let us store this as, I'll store this as U, comma S, comma VT. I will call this as VT. Right, now I can ask it to show what are U, show me S, and then show me VT. Okay, this is my U, this is my S. You can see here in this case there are three singular values, and it is arranged in first one is 31, second one is 2.2, third one is this. So it is already arranging in decreasing order. This is V transpose. Okay, right. So that's what you have. So let me copy paste this in. Okay, right. So we have got this singular value decomposition, and you see it doesn't take much time for this. Of course, if you have large size matrix, it will take little more time, but still it will do. Okay, now let us check whether we have got whatever we have got the singular value. Is it correct? Let us check that. So I will say, let us multiply U into S into VT. This is not, we have to take transpose of this, right? This transpose. Now you can see here, of course, this. So matrix, what was the matrix? First column was 1, 1, 1. Second column was 1, 2, 3, 4, 5. And third column was it's a square. So these are all numerical computations. So it will be, so 0.99999, so many digits is close to 1, right? So it is 1, 1, 1, 1. Next is 1, 2, 3, 4, and so on. So that's correct. That is correct. And what are the singular values? Singular values of this 31 point this. But now let us also verify. So I'll also copy here. Sorry, my cursor is somewhere. I'll copy this one. right? Now we can verify also. Verify meaning what did I said? I said that how to obtain these singular values and then singular vectors, right? Left and right singular vector. So if I look at A dot T transpose times A times A, this is my matrix. Let us call this as let me not A. We are working with M, right? M dot T, the transpose into M. This matrix let us store in M1. This is my M1. So you can see what is M1. This is 3 cross 3 matrix. Now I can find out M1 dot eigen values. M1 dot eigen values. What do you see here? These are going to be squares of sigma 1, sigma 2, sigma 3. That's what you can see, right? This is square root of this. If you take, that will be first singular value, which is 31.20. You can even find out. And the square root. So you just, all you have to do is singular, in order to find singular values, you take the square root of all these things. Similarly, I can find out eigenvectors, M1 dot eigen vectors, right? I have to say, yeah. So this is my first eigenvector with respect to this eigenvalue and so on. So this also, and if you try to compare for example, if you compare this first column of this is going to be first eigenvector. If you compare the second column of this matrix V transpose, that's going to be second column. That's what you're, or some interchange, sometimes it may also happen, or negative multiple of scalar multiple of this. Okay, so you can construct these things very easily. Let me pause for a few seconds so that you can finish this part, then we will go ahead. I think I'll stop sharing entire screen because it unnecessarily kind of distracts. I'll share only the Sage part. This one, yes. So now let us look at how we can do least square solutions. We'll come back to more on singular value decomposition. Let us first finish this least square computation. Can we go ahead? Can we go ahead? Have you all finished whatever we have done? Nimesh has done, good. Who else? 4 people have finished. I am not one of them, I suppose. Harish seems to have finished. Chetan has also finished. Okay. Praveen has also finished. Very good. At least 8 people. If I wait for a few more seconds, there will get many things. Okay, fine. Let us go ahead. Okay, so we want to do least square solutions. So I've already actually prepared, which I have shared already in this. So let me, I'll do it. Here so that you understand. So let us take a what is happening? Let us take some set of points. Let us take some set of points. So these are my points. X is S range -5 to 5, comma 0.5. If you remember, range gives me only arithmetic progression with integer increment. S range you can have non-integer increment also. So here it is varying from -0.5, -5 to 5, and with an increment 0.5. So there will be 20 such points. And then I have a y coordinate, which are 20 numbers. Now we can plot this. Okay, we can plot this. So let me, this also is not needed at present. Okay, let us plot this. So I'm making a data out of it. So a set of x coordinate, y coordinate using this for loop, using list comprehension, and then we will plot. So these are the set of points. So let me copy paste in the Google Sheet. Already you have this in your Google Classroom, but in any way, where is it? So this is now list square. So this is my, this can also go into, okay, fine. Anyway, this is my set of points that I have taken, and then I have made that into data, x coordinate, y coordinate, and we are plotting. Okay, so these are the set of points. Okay, is this clear to everybody?
Sir,
Yes.
sir, so here that points is a function which will help us to point the plots.
This is just we are mentioning x coordinates, y coordinates, and we are plotting all these points.
So we are
have
using the
not
function
defined.
point.
Yeah, point is a function. Yes.
Point is a function.
Points is a function.
Okay.
Yeah, it's not a method. It is a function of this data set of x coordinate, y coordinate. Point size is taken as 20. You can reduce the point size, and it is in red color. If I make it in the other color, you can do. So this is MATLAB. Sorry, C's math plot function. Okay. Now what? Let us say we want to fit cubic to this. We want to fit cubic to this. What is it that we want? We want to fit. We want to fit a cubic. Let us say ax cube, or say y is equal to ax cube, not u, y, ax cube plus bx square plus cx plus d. This is what we want to fit. Okay, so a, b, c, d I will define as a variable, a, b, c, comma, d, and t also as a variable, because instead of x, I will think of that as a variable t, because I have already defined x as the x coordinates. This is how we declare variable. Anything other than x, when you want to do some computation, you have to declare as a variable in Sage. X by default, it understands as a variable, right? So for example, if I want to solve, let us say 2 into x plus 3 into y is equal to 7, and 3 into x minus 2 into y is equal to 6 with respect to, let us say, x and y. And let me also put solution dictionary solution dict equal to true. Have you made some mistake? Oh, x and y I have already declared. So let us call this as A, this as B. This is my A, this is my B, this is A comma B. Yeah. Right now it is giving me the solution as a dictionary. That is how we taught you dictionary. Okay, because all these things becomes very easy when you want to work with the solution. So this is the solution, and what is it? This variable name also I'll copy. Yeah. So many people are copying, pasting. So I see so many pointers in the. Okay, fine. So that's what we have declared, right? Okay. So this was actually not something which is. I'll delete this. I have copied and I'll delete this. Okay. What? So there are we can use our own formula that we found. We can also use inbuilt function. So let us use inbuilt function. Okay, there is inbuilt function called model find fit. Okay, model find fit. So I'll just copy paste there so that I'll just explain. So what is the model we have? Model as a function of t you want to fit. So it is a t cube plus b into t square plus c into t plus d. This is the model. So it will find the model. Okay, and so let me run this part. So it says that it has fitted the model, found the value of a to be this, found the value of b to be this, value of c to be this, value of d to be this. Okay, and then let me also plot. I will also plot the set of points along with the cubic that we have obtained. Okay, this is using find underscore fit, which is an inbuilt function to fit of a curve in Sage Math. Okay, we have not yet used the formula that we have found out. We will come to that in a minute. Let me copy this in Google Sheet, Google Row. Next one is, sorry, I think yeah. Okay, let me pause for a few seconds so that you can finish. So here it is showing you as a dictionary value of A, B, C, D, this parameter approx. Of course, these are approximate values, right? In statistics, they'll call these as approximations. Yeah, some distribution is also involved. Can we go ahead? Can we go ahead?
Sir,
Yes.
one question. Sir,
Yeah,
this
please.
find fit the inbuilt function which plots the graph. That also use the least square technique or some other technique?
See, all are equivalent, so it will use least square technique. One can, now you know how to find the source code of this, right? So you can ask for find underscore fit double question mark. You will also know how the program has been written. At present, let's not worry about what it uses, right?
Okay. Okay,
yeah?
sir.
Yeah. Okay. Am I clear? Okay. We can find out, right? So we can create our own function also, and we can change if it is using least square. I can change it to normal method or other methods, etc. Yeah, of course, it will not just use least square, because finding for arbitrary function, finding derivative, equating it to 0, and then solving will be a lot more difficult. So it will use some other numerical techniques. Okay. Any other question? Any other question? Yes. If you have any question, please let me know. Any question? Okay. Okay. If I don't get question, I get worried, because then it means that people are not following. I don't want that to happen. Okay, fine. So let us go ahead. Now let us look at how we can use other thing that we have described. Let us use normal method. Okay. Remember, we have got the solution as the least square solution as A transpose A, the inverse of that into A transpose Y. Okay. So first, let us find n to be the length of x. We know in this case it is 20, and let us declare the last column was all ones. So I will create one list of 1, 1, 1 n times. That is this. Next, I will create. Let me create first my x1. X1 is already x1 is there, so I don't have to do. But anyway, just to in order to complete, I'll just say x I for I in range n. So this is all x i's. The next one is square. X2 is square and x3 is x cube. Okay. Now, so these are my, and now let us create a matrix A. Let us create a matrix A. What is you can create using column matrix? What is the first column? X3, which is x1 cube, x2 cube, x3 cube. Second column is x1 square, x2 square, x3 square. Third column is x1, x2, x3 up to x20. Last column is all ones. So let us ask it to show what is A. You can see here, this is x1 cube, x2 cube, x2, this is square, then x, and then all 1, 1, 1. Let me, okay. So let me copy this part in the, sorry. This part I have copied. And what is that we have to do? We have to find solution. What is the solution? A transpose. So A into A transpose A dot T is A transpose. Multiply it by A, find its inverse. So this is the inverse of A, multiply by A transpose. And here we have Y should be a vector. So I have converted that into vector, Y as a vector. And then let us look at what is the solution. It says that the solution is, this is my A, this is my B, this is my C, this is my D. And let us compare what we got using inbuilt function. So let us write it here. We had show fit. Now if you compare, your A is this, B is this, C is this, D is this, exactly similar. Of course, it may differ in some points after certain stage, but this is what you'll get. And we can plot using the same thing. Okay, I have copied in the Google Sheet, so please look at. Let me give a pause so that you can do. In case you finish, please click on yes. If you have any doubt, click on raise hand. Ankit has done, very good. Who else has done? Four people have done. Srimanto has done. Good. Does anybody have any difficulty? If you have any difficulty, you can ask. Okay. See, I'm not looking at chat. I'm looking at yes, no, click. Only 6 people have clicked yes. I'm sure many more of you have done. Okay, so this is using inbuilt using the normal method using A transpose A inverse into A transpose B, and we verified that this is same as what we got using inbuilt function find underscore fit. Right? Let us look at using generalized inverse. Right? So Sage already has a function to find generalized inverse. So if I say A dot PSEU pseudo inverse, then it will give me pseudo inverse of this matrix. Of course, it looks ugly at present, but what was the solution? This into Y. So vector I will say, and let us look at this. See that this is my value of A, this is value of B, this is value of C, value of D. So that's exactly what you got as least square. Okay, this is using generalized inverse. Using generalized inverse. Okay, right. You can also do it using singular value decomposition. So let me, I've already written the code. So I will. So we are converting this matrix A into the CDF. Then we are finding a singular value decomposition. I'm calling this because generalized inverse I have to find out. Generalized inverse I have to find out. So this is the generalized inverse using singular value decomposition, and then multiply that by the vector Y, and it should work exactly the same. Okay. So I already explained this. So you can see here, this part is actually finding the generalized inverse, finding the generalized inverse of the rectangular diagonal matrix S, and then find V into S1, which is generalized inverse of S times U transpose times vector V. That's, yeah. So this is exactly same as what we obtained using singular value decomposition. Okay, so I think, yeah. So you can see. Okay, let me again give pause for a few seconds so that you can finish this. The moment you finish, please click yes. So we have verified using inbuilt function find fit, using generalized inverse, which is inbuilt function pseudo inverse, then using the direct formula that we obtained using normal equation A transpose A inverse into A transpose B. Also the generalized inverse found using singular value decomposition. All these things we have verified. I can also do using calculus by finding derivative, but let me, due to paucity of time, let me not get into that part. And of course, I can write numerical methods to solve these things. That can also be done. Is this clear to everybody? Can we go ahead? And if you have to find general least square solution of a matrix of a equation Ax equal to B, you have to define what is A, what is B, and then do the same thing, right? Instead of Ax equal to B, I took the matrix associated with the finding fitting polynomial. Of course, if it is not a polynomial, then this method directly will not work. Okay, because in that case, one has to find what is called non-linear least square. It becomes non-linear least square problem, which has to be done numerically. Otherwise, it's difficult to do. Okay, fine. So let us go ahead. I'll close Sage worksheet. Okay, no clapping. Thank you very much. It's not required. now I'll close this. I will open only the Python notebook. Okay, so let me close this. How do we close? We can close all the automatically Sage worksheets will be saved. You can save it also. You can download. You can go to file and ask it to download as it can download in ASCII format, HTML format, text format, in markdown format, in PDF format, but PDF will require LaTeX installed in your system in .py format. So there are many things that it is there. I have uploaded those files in HTML format so that you can do. Let me just close everything. Oh, that worksheet also got closed. That's something I have to open. Okay, fine. So let me go here. Yeah. Okay, fine. So now what I'm going to do, as I said, we will open Python, pure Python. I can do that in Sage also, but let me get to Python. Okay, so I will close this Sage math by Control C and yes, and then I will exit this. Now using the same thing, I will open Jupyter Notebook. So if you have installed now, all of you please open Jupyter Notebook. Let me open Jupyter Notebook and then I'll share. This I'll go a little fast. So already I have shared in the Google Classroom folder. I have shared a file which has not got name image processing _ SVD _ 2021. So you can open that file. It will open as a HTML file. Okay, right. Let me share this. Okay, fine. So in that folder there is a image called sardar.png. It's a PNG file of Statue of Unity, right? Statue of Unity of Sardar Vallabhbhai Patel. Okay, right. So I've just taken some image, good quality image. That's all. It's nothing like intentional to open this image. Okay, so what we are doing here. So let me import NumPy, numerical Python, which is a very useful command, which is very useful module package. It can do a lot of numerical computations plus all the linear algebra. Many of the Sage computation are done through linalg package in Sage in Python. So it has very nice module of doing linear algebra in Python, that is by NumPy. Then there is another package called PIL for image processing, for image manipulation, and this is for plotting. Okay, right. So let us import all these things. Okay, so let me copy this in the so I should write here. Oh, sorry, wrong one. My cursor is it becomes bold. Okay, so this is importing these packages. Next, we will so first what you do, you download this image and put it in the home directory where you have opened your Jupyter. Mostly it will be in your username, in user home directory of user. Otherwise you'll have to give the complete path. Otherwise you'll have to give the complete path here. So suppose if it is in D, you may have to say D followed by something like that. Okay, Okay, in order to avoid all these things, I have just, so we will load this package. So this package is loaded and it is loading as an image. So it is just after loading, this is plotting. Okay, so you run this. You run this, and next, let me look at what is the size of this. So the size of this figure is 1770 by 995. Okay, absolutely 3-dimensional matrix. Okay, so that's the shape it finds. Now, actually, in order to find singular value decomposition, we will have to convert this into array, numpy array. So that is what is done. So from numpy import as array command, and then convert this image data into array. Please mute yourself. Prachi, please mute.
Sorry.
Yeah, so you convert into array. Okay, and then look at what is the shape of this. This is actually 995 by 1770, and this is by 3. So this is 3-dimensional array. The color image will always be 3-dimensional array. Okay, so let me copy that there. Oh, I think something went wrong. Right, and next, oh, this is same thing. It is coming. Okay, next we will convert this into what is called grayscale image, because at present we have singular value decomposition only for 2-dimensional matrix. One can do it for the color image also. One has to separate into what they call color channels, blue, green, and red channels, and then you can find singular values of those things and then combine. That can be done. Okay, but that will require more time. So we'll convert this into grayscale image. So this is converted into now grayscale. You see only 2-dimension, and then we can plot now. This is the grayscale image of the original image. There are scaling of conversion in terms of RGB. So those things one can do, but this is I'm using inbuilt function. Okay, so this is converting into grayscale image. That is the next part. And then, so this is the plotting of this image. Let me also copy this part. And next, so you can see here what is the shape of this 995 by 1770. Okay, now let us find singular value decomposition of this grayscale image that we have obtained. So this is, you can see here it is finding from NP, that is NumPy library, linalg package, and inside that there is small svd. In says it was capital S, capital V, capital D. Here it is small svd. So that we will do. So you can see, so it took fraction of seconds, but it has done. It has done. Okay. Now let us look at, suppose we want to approximate. So we already saw this A can be written as sigma 1 U1 plus V1 transpose, sigma 1 U1 into V1 transpose plus sigma 2 U2 V2 transpose plus dot, dot, dot. Right. And we can even find out what is rank of this matrix. We can find out what is rank of this matrix. Let us say A, what is this? Image matrix, right? Image mat dot, I think must be NP dot rank. NP dot rank of this. No, think. Anyway, we'll I think it's there somewhere. So rank of this matrix is actually 995. So it's a full rank matrix. Okay. Right. Now, if I take only first two components of this sum, only first two components, and then try to plot. So what we are doing, take the first two component, take only first two columns of U, then first two rows of S, and then first two rows of matrix V transpose, and then plot this. So you can see here, this is the image you are getting. This is the image. Okay, let me copy this there. That's the image you are getting. You can hardly make out what is this image. So it's not a good approximation. Okay, so let us include more. Let us say I will include now 5 components. If I include 5 components, now let us look at what is the image. This is better than the previous one. Let us make it 10 components. 10 components. You can already see that these bars are coming quite clearly, and this image is also appearing. So only 10 components compared to 995. If you look at the figure, the image, the number of elements in that matrix and the number of elements in 10 components, there's huge difference. So the size of the compressed matrix will be very small compared to the original. Right? Now let us take 20 size. It's almost quite clear. You can make out. Right? Those who have know this, we can make out. Now let us make it size 50. This is very good. Right? So you can see that the 50 component has given me very good. Right? I can do this as a nested list. So this is giving me 5 components, 5 singular values, 10 singular values, 50 singular values, 100 singular values, 200 singular values, and so on. Right? So let me copy that part there. Yeah. And if you look at actually the size, what was the let's look at for example 20 components. I don't want this one. If I look at the 20 components, then what do we have? So let us say K is equal to 20. Then the size of the matrix, first one will be, you have the sigma 1. So 1 plus, then U transpose. Sorry, U will have size what? 995, right? And V has, what is, it was 1770, right? I can write M and N. I think I wrote somewhere M and N, but 1770. I'm doing it manually. 1770. This times 20. Yeah, this time 20. This is the number of entries that we require in order to do this approximation. Whereas what was the size of the the original image? It was, wait, why are we multiplying? This should be add, right? Sorry, I'm sorry. They have to add. So 995 components for U1, 1770 for the V1, and plus 1 for sigma 1, and this 20 of such. So that's what I was wondering, why it is coming so large. This, whereas original size was this into this. So you can see here what is the difference in terms of the size of the matrix, the compressed figure, and other things. There's a huge difference. Okay, so that is one application of singular value decomposition. This is also called in machine learning a dimensionality reduction problem. Right? So out of 995, let us say parameters, you have reduced to 20 and you have got very good result. Okay. And the similar concept is done using principal component analysis. I'll not get into that. It's there in this sheet. Okay. Singular principal component analysis. That is also called classification problem. Sorry, dimensionality reduction problem. Okay. These are all very much useful in machine learning, data analysis, artificial intelligence. Of course, you can use it for many other applications also, but this is one which is quite appealing. And you see that this can be explained very easily. Anybody who knows eigenvalues, eigenvectors can explain. Any first year engineering student by end of the first year, they would have learned about eigenvalues, eigenvectors. So this kind of applications can be very easily explained. And in case you are teaching and if you want to use these kind of tools, you can really do very nicely. And student can do on their mobile also these things. As you saw in Professor Sanguli told us how much that he does on the mobile phone and other things. So it can be done. So one, it brings lot of pedagogical benefits for teaching this kind of tool, and no money is required, right, to buy. Second, you can do lot of problems even in the class, which is difficult to do by hand. By hand, I mean, I will be surprised if any of you at any point of time found eigenvalues, eigenvectors of 4x4 arbitrary matrix in your class. I will be very surprised. Okay, even the inverse, finding inverse of 4x4 matrix, you would not even venture to this. But using this kind of tools can be very easily done. Okay, right. So this is an application of singular value decomposition, which is application which I did is called dimensionality reduction. Okay, right. So let us also, I don't know, I have only some 7 minutes. If you have any questions first, please ask. If you have any questions. In case you are having any question. Any of you?
Sir, there is any connection between least square method and,
And?
fitting the curve, sir?
Fitting the
scatter diagram, fitting curve, regression line, regression curve.
What I was doing, I fitted cubic. So
Yes,
instead of cubic, if you take 1 degree, it is a line, right?
line. Okay, sir. Okay, sir. The
Right,
parabola,
so
everything we can do, sir.
Yes, of course, I did it for cubic.
Yes,
So
sir.
instead of cubic, you can stop at quadratic.
Line and the quadratic. Okay, sir. Okay, sir.
Yeah, I purposely did for 3 so that line and quadratic will be much easier. Okay, any other question? Any other question? Maybe it's too simple. What I'm doing is very simple, right? So that's fine, I think. Let me very quickly explain clustering. This actually you can find it on this particular website. So I'll just quickly. Clustering is another technique which actually doesn't require any mathematics more than high school. And this is what is called classification techniques. Okay, so you can classify the data in various categories. For example, segmentation. So let's say these are a lot of applications. For example, if let us say bank wants to understand whom to give loan, not to give loan, etc., they can use this classification technique. Or in shops, right? They can use. And all of us are getting these days a lot of advertisement for on our email, etc., right? Or the moment you start searching for, let us say, to buy some mobile, next few days you will get mobile advertisement. How do they know? How do they know? So they do this kind of segmentations. By looking at your surfing behavior, surfing patterns, they'll find out. And then there are people back end who are sitting and then doing these kind of things. So we may not know, but we are watched by these people, right? And giving few of our information, we do hue and cry, but without knowing many things are being, Google is watching, keeping eye on us. But anyway, those are separate issues, right? So so what it does is this. I'll explain using this algorithm. So let me run. Since I have already shared, I will not copy paste. So first you have some set of data. Okay, let us. I have loaded this data. So we have, this is set of data. Okay, now you want to classify this data into various categories. Already you can see it is 2 colors, but anyway, that is by default. Okay, so let us say we want to cluster this into 3 segments. Classify this into 3 segments. Okay, so what we can do is we can start with some 3 points, arbitrary 3 points. Okay, so this is the plot, arbitrary 3 points. So this you can see arbitrary 3 points you have started with. And then now look at the points which are close. So these are the 3 centers, let us say 3 centroid I have called centers. Look at, classify all these points which are closest to this. So if I, for example, this point will be closest to this, so this goes in the first cluster. This point, these points are closest to this, will go in second cluster, and so on, right? So next stage is to compute all these indices, and then now once you have after getting initial centroid, you do what you do. You look at the indices or the points which are close to whichever of the centroid, put them in one box. Then second one, put them in another box. Third one, put them in another box. Then you find centroid of those in one box. Whatever the points, you find the centroid. Take centroid is nothing but taking the average, right? And then you get a new centroid. And then again repeat this process. Keep on repeating this process. You will get these clusters, 3 clusters in this case, and that is what is called clustering. This is called k-means clustering. There are other different clustering techniques. This is one of the most popular one, k-means. So all it requires is Euclidean distance. You can do with other distance also, but here we are using Euclidean distance. That's all. So any high school student can do this, right? Any high school student can do this. It's an application of distance, let us say, right? Yeah. So this is what we did. So after one iterate, you can see that the clusters have changed. This is one. I think this was the initial one, I suppose. Yeah, this is the first. After first, let us do 2 times. And then you can see here, now this black one, they have changed. Next, let us do 3 times. Yeah. Now let us do this 20 times, and then let us see. Now you can see here the centroid. You can see here the center has become here. All these blue points are in this cluster. All red points are in this cluster. Green ones are in this cluster. That is what is called clustering. That's what is called clustering. So you can run these codes on your own. I have given you, and I think there is also a website. I think I'll share on that website. It is, you can actually do. It gives you the live how it clusters. Okay, so you can generate random points and then give how many clusters you want and then run. So it will animate and show you how it clusters, how these centroids are moving. Okay, so that is what is called clustering. Okay, and you can run this. I'll share that the link. I think I have somewhere. Let me Just see. No, I don't think I have it here. Okay, well, check it out. I'll share that link anyway. Okay, so I think let me stop. It's already 3:30, but if you have some questions, please go ahead. If you have some questions, please go ahead and ask.
Sir, I have a silly question, sir.
Yes, no question is silly, madam.
Sir, how could I find out the number of clusters? Just like your example 3.
Right. So there are some certain methods how to find how many clusters we can start with. There are some called elbow method and other things, etc. So I didn't go into those details because you're not doing course on clustering, but there are methods you can look at. But see, basically, by once you have at least plotted the data, etc., you can always find out. But in marketing, etc., already it is decided how many clusters they want to classify into, right? Right. So if they have to provide loan based on the incomes and expenditure, they already do decide if you have this much credit score, I'll give loan or I'll not give loan, right? So many times it is pre-decided, but there are methods using which one can find out how many clusters, especially if you have unknown data where you don't have anything to bank on from the previous history. There you can decide using these methods. But those methods are, again, I mean, nothing is foolproof kind of thing. But it is some kind. It works. I mean, as far as you know, yeah. Okay. Any other questions? I hope I have answered you, madam.
Yes, sir. Yes, sir.
Yeah. Any other question?